In this video, we shall explore one of the nuances of method overriding. This illustrates that even method calls originating from within the superclass part of an object are resolved within the context of the dynamic type of the object. We shall use version 2 of the Foxes and Rabbits project for this exploration. Version 2 of the project introduced a superclass for Fox and Rabbit called Animal. Animal is an abstract class because its act method has no body. This is because no worthwhile common functionality was found in the hunt and run methods of Fox and Rabbit to place in act. The simulate one step method of simulator calls the abstract act method, and the dynamic type of the animal variable is then used to select the correct concrete version of the act method. This is according to the standard rules of polymorphism and method lookup that were covered in the previous chapter. In this version of the project, there are still significant amounts of common code in Fox and Rabbit that we would like to move to the superclass. In particular, it would be good to move those aspects relating to the age of an animal. The Rabbit class defines an age field. This is then initialized in the constructor. Incremented in increment age, possibly resulting in the death of a rabbit, and its value is checked in can breed against the minimum breeding age. The Fox class defines almost identical code, which we won't show here. The main reason for not moving this code to the animal class is the fact that seemingly identical looking methods are not actually identical. For example, although both can breed methods test the current age against the static breeding age variable, foxes and rabbits have different values for that variable. The value of that variable cannot be set in the animal class because it would not be valid for all subclasses. We need to find a way around this if we're to successfully move much of the common age-related code to the superclass. In this version of the project, we've begun to shift the age-related code, but so far we've largely just moved the field and provided protected get, set and increment methods for it. In Rabbit and Fox, direct accesses to the field have been replaced by calls to these methods. For instance, when setting an initial random age in the constructor and an increment age. Notice that we could not move the full code of increment age because it suffers from the same issue as can breed. Max age is a class variable with different values in the two subclasses. However, once we fix the problem for can breed, we shall be able to apply the same solution for increment age. This version of the project compiles and runs as normal. So let's now move the can breed method from rabbit to animal and remove it from fox. Clearly this won't compile because we don't have a breeding age variable in the animal class. What can the age be compared against to determine whether an animal can breed or not? We need to appreciate that the can breed method will have been called on a particular individual within the simulation. That individual will have a particular current age and a breeding age corresponding to its dynamic type, and therein lies the solution. We need an answer to the breeding age question that depends on the dynamic type of the object whose can breed method has been called. The way to get the answer is to call a method that's been defined in the subclass. In other words, if we have a get breeding age method in the subclasses of animal, then it will return the breeding age that applies to a particular individual. So let's replace breeding age with a call to get breeding age. And then define appropriate versions of the method in both subclasses, like this one here. However, when we try to compile, we have a problem. The compiler cannot find get breeding age in animal. You probably recognize that this is exactly the same problem as we saw with the display method of the network project. It's a reminder that the compiler works with the static type when checking method calls rather than the dynamic type. Here the static type is animal, so the compiler expects animal, or one of its superclasses, to have a get breeding age method, which it doesn't. So we clearly have to define one in animal. But once again we find ourselves defining a method with no sensible implementation. Animals don't have their own breeding age, that only applies to subclasses. So we make the method abstract in animal. That will also guarantee that every subclass defines a version of the method to be called when required by canBreed. Now the project compiles. By now you should have got used to the fact that a call to a method on a variable of a given static type is resolved from the dynamic type of the object it refers to, and looking for the method starting from the lowest point in its inheritance hierarchy and then working up the hierarchy until a match is found. What is particularly interesting to consider is that those same rules apply even to method calls originating within an object, and not just for method calls made on a variable that originate external to an object. The call here to get breeding age originates midway up the inheritance hierarchy in the animal class, yet the lookup process at runtime starts from the lowest point. This can easily be illustrated by setting a breakpoint in the canBreed method. When we step into the canBreed method, we can see from the debugger's call sequence that we were in the fox's breed method, which called the animal's canBreed method, and now we're in the fox's getBreedingAge method, and all of those calls have still to complete. While it might seem obvious that the local copy of getBreedingAge in animal could not have been called, because it's an abstract method, the same rule would have applied even if the method were not abstract. In fact, we have a danger of inheritance revealed here. Often when we write calls to local methods within the same class, we don't give any thought to the fact that a subclass might override the method we're calling and fundamentally change the logic of what then happens. This can make a nonsense of any contract a class is meant to fulfill. However, here that feature of polymorphism is very useful. There's now nothing to stop us moving all of the age-related common code from fox and rabbit to animal using a similar technique. In summary, we've seen that method overriding allows us to refactor even more of the common code from the animal subclasses than we'd previously thought possible. Method calls originating internally within an object follow the same rules on method lookup that apply when methods are called externally. However, while this is a powerful and useful feature, it's not without some danger.